Me today is, ooh, that's very loud. And with me today is Narayan from Intuit, and we're going to be guiding you through this journey of how to do this. And special thanks for showing up at this late on a Thursday right before the party, because I know everyone's getting really tired. So you have a monolith. What are you doing? Wait, not that kind of monolith, this kind of monolith. You got a really big database. And there's lots of different ways to think about monoliths, right? Because they're just something that's kind of a little bit out of control from a database perspective. And in this case, I've got a lot of different applications talking to one database. I got a lot of different data that's in the one database, right? So this is what I classically think, but there could be lots of different examples of what a monolith is. Let's dive into this example a little more detail. So you might have small isolated workloads running, and we had a lot of these at Amazon when I first started. And this is like an unrelated thing that's just co-housed with the database. So in this case, it's our supplier app. It's got a few tables. It's not that big. It doesn't work. It doesn't do that much stuff, but it's there, right? So why do we end up like this? Well, you might have had a licensing challenge because you were on a commercial database, so you didn't want to buy another license. Might have just been that you had a resource. You got a box, right? Throw it on there. And another one was at the time, you didn't want to have another database to manage because that was challenging, right? So just throw it in together. But the problem with that is, you can have problems where that table gets out of control, right? Or you just get bad queries on it unrelated to your main application. So even though it doesn't usually use a lot of CPU, it could. And this can cause disruption. And there's, you also got to talk to people about when you can do maintenance because they might have different maintenance windows and all that kind of fun stuff, right? So not a great thing to have in your database if you don't need it. The next one's a little more challenging. This is what I call an entangled workload. So this is where you have multiple applications typically, sometimes in the same app or sometimes spread out across different deployments that are talking to a set of data where it's all together, right? In this case, it's customers' orders and our shipping, right? And the same reasons that we had before, we have, except for now we have another reason, which was it was very easy for the developers to do this, right? Because it's so much easier to write these apps when you don't have to go figure out where the shipping data is if you're in the ordering system, right? It's just in the same database. So you see a lot of databases get created this way. The problem with this, and this is one that a lot of leadership misses, is that you've got shared state now, right? And what do I mean by that? If the shipping team decides to make a table change to one of the shipping tables, right? Adds a column and they don't coordinate with the other team, bam, you got an outage, right? This is horrible. So what does that mean? That means you got to do shared QA, shared testing, right? Shared certification. That's going to increase your errors, decrease your velocity, and as you have more and more developers working on these systems, it's going to become more and more challenging, right? So you really want to get rid of that shared state, and we'll show you how to do that in a bit. The other one that isn't sort of as commonly thought about is sort of temporal data. So over time, as your database has been growing and living, right, especially in the ordering world, you just keep getting more and more orders, right? So to start with, when you store an order, right, and I'm just going to talk about sort of the heap portion of the storage, not indexes, but you can imagine the indexes here. When you have an order come in, it's going to go into a block, right? And that block's going to get filled up with other things at that time. But to find that order, it's really cheap, right? You just got to go get that one block. But another order comes in a couple weeks later into a new block, right? So again, still cheap to find it. So this query is very predictable. So that's great, right? Over time, we have lots of orders, right, for that same customer, but it's still cheap. So no problem, right? Except for you have queries like this. Find me all my orders for the last year. And now this costs 10 times as much, right? But that's really a simplistic example because in our system, for each order we have 3 order items and 2 item details per order item, right? So that actually means we're grabbing more like 100 blocks on this query. And I remember back in the days at Amazon, we had some customers where we were literally gathering like tens of thousands of blocks to go answer the query of, show me my orders from last year or the last couple of years, right? So this is quite painful, and it destabilizes your system because these large queries start almost looking like reporting queries, not things that you'd run on your main application. So that's kind of another problem with sort of the monoliths, right? And then the last one I want to talk about is sort of an asymmetric workload. And what do I mean by asymmetric? It means something that's not really core to what you're doing with the main application. In this case, analytics. Could be other things, could be search. There's lots of different examples. But you might be doing data warehousing, decision support, or running real-time dashboards against your OLTP system. That sounds good, right? Because I don't have to do any ETL. My data's all up to date, right? There's no lag. The business leaders are happy. But guess what happens? You have these queries that are doing massive things against your database where it's going to be destabilizing, right? Large scans, large sorts. And that's what I mean by it's asymmetric, because it's not these point select small joins. And again, CPU I/O, memory usage can all be completely destabilized by just someone running a bad one of these queries, and I'm sure most of us have had that happen to us. So now that I've sort of talked about the basis of the monolith, I want to invite Narayan up to talk about Intuit's story and their journey, and then after that, I'll come back and we'll talk more.
Thank you, Grant. Good afternoon. My name is Narayanan Gopalakrishnan. I'm a principal engineer at Intuit. And it's my pleasure to walk through the journey of QuickBooks modernization with you and share some of the recipes behind its success. First, a quick introduction to Intuit. We are an AI-powered fintech platform serving consumers, small business, and mid-market customers through TurboTax, Credit Karma, QuickBooks, and MailChimp. When I say QuickBooks, you may think of bookkeeping or accounting, but QuickBooks does a lot more than accounting today. As you see the feature breadth we have, accounting is one of the many things. Our platform helps you manage business, and accounting happens along the way. And we do this at a massive scale. Over 10 million small and mid-market customers use QuickBooks, and we recently launched our enterprise offering. With that, let's start looking at our legacy architecture. QuickBooks is a Java application deployed on Kubernetes. It was using a commercial database on relational backend. And we deploy this in a swim lane architecture, and let me define what it is. A swim lane is a single independent deployment of our application with the database, basically our version of a cell-based architecture. We use this for two reasons. One is scalability. As we need to scale the system, we can keep adding swim lanes and scale horizontally. The second is geo-partitioning. As we have a global customer base, this allows us to host customers from different regions in different swim lanes and possibly even deploy in different AWS regions. And today, we have a fleet of these to manage our 10 million customers. Our databases manage hundreds of terabytes of data, was using over 1 million provisioned IOPS, and running OLTP, OLAP search use cases on relational. The application has millions of lines of code, thousands of dynamic queries, several complex queries. We have a homegrown database schema generator and a data access and dynamic SQL generator. All of this was designed to work with our legacy database and optimized using several database features. Now, let's take a look at the need for modernization. So as QuickBooks evolved and we kept adding features, over time, it grew into this monolith. And what were the challenges? So over time, it was getting difficult to scale, especially for some of our large customers. And also for our next chapter of growth, where we want to handle 10 times the data we currently have. It was also slowing down our development velocity, and it was getting increasingly expensive to manage it. So to address these, we decided to switch to a service-based architecture using cloud-native open source databases. And that gave us a blueprint for our target architecture that looks like this. As you can see, this architecture allows us to choose from a number of databases based on the use case rather than a one-size-fits-all. Now let's look at the requirements. So our goal was to take this monolithic system and transform to this architecture, but do this with minimal disruption for our 10 million customers, with 100% data parity and feature parity, with full support for fallback, and improve our performance and resilience, and finish it by a fixed end date based on our licensing. And we had to do all this while we continue to develop features and ship to our customers. So in a way, this was like changing an aircraft's engine while still flying. Is that sounding exciting? Let's take a look at how we approached it. So we took a phased approach, starting with evaluating technologies based on a set of features we were looking for to support our product. And based on the feasibility, we defined the scope of what we are going to change, had some high-level technical design, and had a planning phase. And then started working on the actual execution, doing schema conversion, data migration, and application conversion. We did extensive testing and had a careful rollout strategy to complete it. Now, let's go through each of these phases and look at some of the decisions we made and some key takeaways. Let's start with the evaluation phase. So as a SaaS application, one of our foundational requirements is multi-tenancy. Let's do a quick primer on this topic. So as you may know, there are 3 basic models for implementing multi-tenancy in the database. The first is a silo model, where you have a dedicated database per customer. This gives the highest level of isolation. It also comes with high operational overhead. So this is a good option if you have a limited number of tenants. The second option is the bridge model, where a single database is shared by multiple tenants, but each having a dedicated schema. This is a good trade-off between data isolation and operational overhead. In fact, QuickBooks started with this model in its early days, and we soon realized we had to grow out of it because it doesn't scale for millions of tenants. And it took us to the third model, which is a pool model. So in the pool model, you have a single database schema shared by several tenants. This is great for scaling for a large number of tenants at low operational overhead, but it doesn't have high data isolation. So to address these concerns, as we switched from bridge model to pool model, we followed certain schema design principles in the database and implemented a layer to guarantee data isolation and also make our tenancy model transparent to the application. And these principles have served us very well in the long run. Now let's take a look at some of the other features we're looking for. We have tables with billions of rows and tables with temporal data, and we need commercial-grade partitioning to manage it. We want to be able to make complex schema changes without downtime to continue developing features, so we need an online schema evaluation. We need the full power of SQL to implement all the complex query use cases we had in the system. We need tools and techniques to tune those complex queries to make sure they are performant. And more importantly, once you tune them, ensure that performance is consistent over time, which is where query plan stability is critical. And then we needed the database to scale to thousands of connections to handle our load. So based on these features and a careful evaluation, we chose Aurora Postgres. Postgres for row-level security and some of the other features it has that we are looking for, and Aurora for scalability, HA, and DR, and more importantly, the Aurora query plan management, which gives us the much-needed query plan stability we were looking for. Now let's take a look at our execution. Since we have a homegrown schema generator, we added support for Postgres in our schema generator and implemented some rules around data type mapping based on Postgres best practices. And this is a very important step. And then we converted triggers and stored procedures, which we didn't have too many, and started working on data migration. And for some of the critical features, we did extensive POCs to make sure those features work as expected for our use case, but also can perform and scale. And as the application was written for the legacy database, the first thing we did was introduce a SQL abstraction layer and refactored all our data access behind it, so developers could continue writing application without worrying about the database. And then we added support for Postgres to our dynamic query generation and code generation tools and put it behind the same abstraction. So developers could continue working without worrying about the database, and we could do parallel builds and deploys on both the legacy stack and the target stack. And this allowed us to continue doing these refactorings while we continue to develop features on the product. Now let's take a look at data migration. We chose DMS for our data migration and used a couple of patterns from DMS playbook. The first pattern we used is the fall forward pattern. The way it works is you have replication from your source to target Aurora using DMS, and then you set up another leg of replication from this target Aurora to a clone of your source database. The benefit of doing this is you are continuously testing the full pipeline, and if there are data issues during replication, you have your source database still intact. The second pattern we used was the fallback pattern. It starts with an identical source to target via DMS, but once you do the cutover to the target, you start replicating in the reverse direction, back to your source. The challenge with this is you are testing this side of the pipeline only when you are live on Aurora, And if you have issues and you need to fall back, you may have data loss. Since QuickBooks uses multiple swim lanes, we use the first pattern for the initial set of swim lanes. And once we gain confidence, we switch to the second pattern for efficiency. Now, with all these changes, a brand new database and a completely refactored data access code, testing the system for both functional and performance was a huge challenge, and we didn't have a lot of time left. And that's where we came up with an innovative approach using a capture replay technique, and that was a game changer. Let's take a look at how this works. So we have our application running in production. We added some lightweight instrumentation to capture every query it executes on the bind variables and caught them in a queue. And we ran it through our dynamic query generation component to convert every legacy query to its corresponding Postgres query. And then we stored them in a repository. With this, we could capture millions and millions of queries from our production workload, convert the legacy queries to corresponding Postgres queries, and store it in this repository. With this, we started working on a replay. To do the replay, we set up a clone of our production environment by setting up continuous replication from our production database to both the source as well as target engines with the continuous replication. With this, we could replay the captured queries again through a queue, and the queue workers replayed the legacy as well as Postgres queries against the corresponding engines. And they did two things. For every query they executed, they checked the results row by row, column by column to see if there are functional differences. They also collected performance metrics, SQL performance metrics, to identify areas that needed tuning. We did this over 100 times to find a number of functional performance issues. We also used this technique to test our target system under different configurations before we went live. And this gave us the confidence to move to the next phase, which is the rollout. So we used a progressive rollout phase, starting with a 4-hour rollout during off-peak hours. So the idea is to start with just testing the waters, see how the new system behaves during off-peak hours, and then monitor and do a planned switchback within 4 hours, in 4 hours. Then we try a 24-hour rollout, this time handling peak hour traffic. We continue to monitor how the system behaves during 24 hours for health and stability. And we do a planned switchback in 24 hours. Then we take these learnings and do a 1-week rollout. This time the goal is to stay on the target system unless there are unexpected issues. And based on these learnings, we started doing the cutover for the initial set of swim lanes. We had a 2-week rollback period, meaning we are replicating data back for up to 2 weeks, and then we could cut the cord, so to say. And then for the remaining swim lanes, it was just a rinse and repeat and scaling the process and completed. So one of our proudest accomplishments in this project is we had 0 unplanned switchbacks in this entire process because of the meticulous testing done through capture replay. And the rollout process was flawless, and we could complete migrating all of our swim lanes on time. Now let's look at the benefits and results. So with Aurora, we have better scalability, especially for a read-heavy system like QuickBooks. Using multiple readers is giving us much better scalability. We also have HA, and using Aurora Global, we have DR out of the box, and we are able to do one-click disaster recovery drills using Aurora Global. So we switched search from relational to open search, and that has unlocked our ability to go beyond simple text search and do semantic and hybrid search. And this is powering some of the AI use cases in the product. We built audit as a reusable service in the ecosystem. And this has unlocked some interesting fraud and anomaly detection capabilities, and also unlocking some Gen AI use cases. Plan stability was a pleasant surprise for us, as we had better plan stability on Postgres, and we had much fewer unexpected spikes due to plan flips. I'd like to take a moment to thank the Aurora QPM team for the great partnership they had and all the features and enhancements they made to QPM to support our use cases. And by switching from paying for millions of provisioned IOPS to a pay-per-use model, we are saving on hosting cost. So in summary, we have better scale and velocity at lower cost. Now, what's next for us? So with a service-based architecture, we have a number of databases from where we need to integrate data. And we are looking at using zero ETL for that. With a large fleet of databases we manage, doing version upgrade takes up a lot of effort, and we are looking at blue-green for making that simple. And while the homegrown sharding works great for us, it is still a lot of undifferentiated heavy lifting. We are looking at leveraging Aurora Limitless as a managed sharding solution. And before I pass it back to Grant, I'd like to thank the entire team from Intuit that was part of this amazing journey. As you can imagine, this was not easy. It was full of challenges, but it was the team's passion and commitment that got us through every single challenge. Also, I'd like to thank AWS for their awesome partnership throughout this journey. Hope that was insightful. Thanks for your time, and I'll pass it back to Grant.
Thanks, Narayan. So we're going to dive a little bit into some of the services that Narayan talked about that they used and that we think are useful on this kind of path, this migration. So the first is DMS. I have a fun story about how we had a lot of discussions about whether it should be called a migration service or a replication service, because it kind of does both. The first thing I'm going to talk about is mostly migration, and that's why we ended up naming it as it is, because it does a lot of things that help you with migration. If you are moving from one engine to a new engine, from like the commercial to open source, we have this really good schema conversion tool that can allow you to really analyze your schema, tell you what's going to be different, find out what the problems are, and help you get to the new system. But that's just part of the solution, right? So for the whole conversion, you start with your source database, you get your target on the end, and there's a lot of steps, right? But DMS can really help you get there completely. The first thing it does, it can do assessment, so it can see all the databases you have, look at all the code, and really tell you what's going on. Then it can use that schema conversion tool to get you a new schema. Now, some of this stuff includes stored procedure code that can be quite complex. We now have a GenAI integration that really helps with some of the more complicated code that was really tough for us to convert in the past. And then the last step is that step that Narayan was showing where you're using it as a replication tool to go from the source to the target and replicate both that new schema and that data inbound. So that's only half of it, though. That's only half the picture, because that's just your data. You might have your target, but you don't have your application yet. So you need to do your application. And this, again, is where Q Developer can come in and can help you actually do conversion using the schema that you've got from the schema conversion tool to help update your applications to become useful for that new database. And, of course, you can skip a lot of this if you're going from the same engine to the same engine, and you just can use DMS for the replication, as you'll see in a second. So as I was saying, it can be a replication service. We got our target on the left, the destination on the right, DMS in the middle. It does a full load, so it dumps all the data, loads it in, and then it does CDC, logical replication, to catch up. And once you're caught up, you can basically switch. Now, that's not the end of the story, though, for using DMS. You can use it as part of your microservice architecture. You can actually fan out data. Now that you're running from Aurora, it can replicate to DMS. You can replicate to other Aurora databases or various services that we have, or things of your own, right? Other applications. So this is really a way to not just to have tight coupling between your systems. So it's another very useful tool in the journey. So of course, I've got to talk about Amazon Aurora. That's kind of the thing I do on a daily basis, but it really is a purpose-built database for the cloud. It's fully MySQL and fully Postgres compatible, not at the same time. That would be weird. So you can have either mode. You can run it either way, depending on what engine you like, because we believe that every engine has its benefits. So the commonality, though, is these aspects like performance, scalability, the availability, the durability, the secure, and the fully managed. And the fully managed is one of the key things that when we started RDS and now Aurora is really key to going to microservices, because you're going to end up with more databases, which means you have to get to something that's easier to manage than the classic systems, right? So let's dive in a little bit to the architecture, what makes Aurora different, and what I hope is better for you. So we start with storage, and that blue line is sort of your virtual volume you get for your database. And it spans across 3 availability zones, and this is for durability. The yellow boxes are our storage servers. I'm showing 9 of them, but it could be thousands or tens of thousands in a particular region. So you get your first database instance against your storage cluster, and that's the thing that you're going to use with most of your applications. And the first difference is that we write log records. We don't write blocks. And there's a lot of advantages to this. We don't have to do checkpointing. We do a lot less work on that head node. And you'll see that we write to 6 places, and those are the little rings. Now, each of those is a 10 gig chunk. We're not writing 10 gig chunks, but that's our organizational unit in storage. So we need 4 of 6 of those writes. So when you see 2 in each availability zone, so we need 4 of those to complete before you're going to get an ACK on commit. We do that on all things, but we don't actually have to wait on writes because we know before commit we can move forward. So it means that we get very good performance, but you have full durability. But we want to make things simple and not have to change too much of the code of the great open source systems, so we actually read back blocks. So we change from logs, we apply those to the blocks, and we ship back blocks when we need to read them. So this makes the database nice and simple and reliable. So sometimes you might have a write that got missed. So that's that little red circle. That one might not have got an update. Well, we do a whole bunch of cleaning and testing behind the scenes to make sure that we have all the data. So if we lose a write, one of the peers will just do peer-to-peer replication and correct that. If we have a failure in our storage unit, we will just replicate a new copy to a new storage unit. So all this happens behind the scenes. You don't have to do anything. It's very nice. And the other major differentiator, as Narayan was saying, is we have these read-only nodes that can really help you with read scalability, and you don't have to buy more storage for each one of these that you get. So that can save you a lot of money. And you can have up to 15 of these in whatever kind of configuration you want across the region. And I'm showing that each one of mine is actually a different instance type. So I have Graviton on the one side, Intel in the middle, and serverless. So you can mix and match whatever size and configuration you want. And this is a great way where if you want to switch from, let's say, Intel to Graviton, you can just fail over between them and test. And then if you don't, if you're like, oh, that didn't really wasn't as fast or whatever, you can switch back. But for the most part, you're probably going to be happy there. So now the other one that's really nice, again, for manageability is our storage. It grows and shrinks depending on what you're using. So you no longer have to, like a file system, be like, oh, I got to allocate a whole bunch of storage I don't need just so I don't run out. So that's another nice manageability feature. In the case of a failure of like a DB instance in that middle availability zone, we're going to fail over to one of the read-only nodes, and this takes less than a minute to happen, and you're back up and running, again, fully durable. And we have some nice wrapper drivers that can actually bring that down because some of that time is DNS propagation. Now this architecture allows us to do really neat things, and one of them is global database. So global database allows you to have DR across regions. What we do here is we create a volume in the other region, and we start replication through these replication servers and agents between these two systems. And this is storage-based replication, so you'll notice I don't need an instance on the other side, so you're not paying for something you're not using. So when you do a write, just like normal, it's got to update the read-only nodes, it's going to go to storage in the local storage, it's going to go to this replication server, that's going to forward it to the agent, over to the storage on the other side, and at that point, you're good from a DR perspective. So your boss is happy because they have DR, and you're not paying for a doubling of your system. But if you do want read-only nodes, we do support that. So you can actually, from the replication server, it's going to keep that read-only node updated. So you can actually use it for applications over there for read scaling, as Narayan said. So this allows you to actually do read scaling on a global basis, and you can have up to 5 destination regions close to your customer. Now, another piece of the sort of manageability puzzle is query tuning, making sure your thing is performing well. Performance insights on Aurora, and we have performance insights across RDS and Aurora, but I'm going to show it just for Aurora here, allows you to visualize what's going on with your database and your queries. So that green box is, the green color is for CPU. So as you can see, at a certain point, my CPU kind of goes crazy, and I actually hit sort of 100% CPU on this, and that's not going to be very good for my application. But I can drill into that, and I can say, what's going on there? And I can see it's this specific query. So now we know what changed. We don't know why. So let's go and look and say, an older period. Let's go look a few minutes before that problem. Oh no, it wasn't using that much CPU, so something changed, right? This is always bad. So let's look at what the plans are. So before we were doing some bitmap and some nested loops, and now we're doing things like hash joins, sequential scans. It's like horrible, right? Way more expensive. Now this can change because of stats changes, and you didn't analyze, config change, maybe an index change can change your plans. Now, in my case, it happened to be because I turned off 2 of the planner features, is not something that I would advise, but it's very good for doing demos. This is where query plan management comes in, and that was one of the things that Narayan talked about. We call it QPM. This is for plan stability. So we capture statements. So as you're running statements, we're seeing two different queries here, query A and query B, and we got their plans. So we like those plans. They look good to us. So we approve the plans, and that gets us a baseline. And what this means is that's the plans that are going to be used. So even when another plan is generated by the planner, it won't be used. But we do keep them so that if, let's say, a third version of that plan comes in, and it is actually now better because, let's say, the data volume has changed, we can compare those plans and evolve our system and basically promote that plan to being the active one, right? So this isn't a static one-time thing. You can evolve your system, but if you don't need to, you can just keep your plans, right? So this is really important for if you've got a lot of systems and you don't want to have to worry about plan changes. And this is the result. I enabled QPM and my stable plans, and of course I just go back to my plans. Even though I have those planner settings still disabled at the instance level, everything is still working. So that's how well this works. One of the enhancements we did, as part of the ask for Intuit was that we could do this on read-only nodes as well, because originally it was just on the read-write. But of course that makes sense. Why wouldn't it also want to work on the read-only nodes? So we've also done some other nice features to really kind of improve performance or price performance for a lot of folks. And that's a tiered cache if you're doing a lot of reading from storage. So if you have a large working set size and you want faster reads. So Postgres normally, it's going to read from shared buffers if the block is there, and it's just going to get a nice fast reply. If it's not there, it's going to come from storage, and that's going to take a little longer. And if you do this occasionally, it's kind of fine. But if you do it a lot, that's probably going to affect your application performance. So what we can do now is we can have a tiered cache. If you're using the IO-optimized storage SKU, we now have this tiered cache option. And all you have to do is order the different instance types, the R6GD or R6ID. That's always very tough to say quickly, for these Aurora versions or higher. And we use part of this for caching temporary objects, like so for spill. So you get faster sorting when you have to spill larger than memory. But the main use case is for a tiered cache that is actually 4 times the size of main memory. So how do we do this? Well, we use a little bit of the shared buffers as metadata. And now we're going to check in that metadata before we do reads. So if it's not in cache, we read the block in a cache. And notice we haven't touched the tiered cache. We haven't changed the read path. We don't want to make any complexity there, right? So got your read, fine. It's in shared buffers. At some point, you stop reading that block. It's going to get ejected. This is where we move it to the tiered cache on eviction asynchronously, so it doesn't affect your regular processing. We update your metadata so that we know it's in tiered cache. So the next time we ask, we go and say, is it in the tiered cache? Yes, it is. Boom, it's read. Now, the main challenge you have with these kind of systems is when you do updates on a tiered cache, with checkpointing and everything, it gets very complicated because you've got to destage and do a bunch of stuff while you're checkpointing. But remember, we don't do checkpointing with Aurora, so we don't have this problem. So when we do an update for invalidation, all we have to do is invalidate the metadata. And that's it. We don't have to go touch the tiered cache. So we're not doing a lot of excess writes to the cache to burn out that NVMe. So this is very efficient. So this allows for really nice performance. So let's look at that performance difference. So what I have here is I have sysbench. It's a read-only point select, very simple workload. Uniform distribution, which is not the normal sysbench one. So that means it's going to read all the blocks, right? It's not just going to concentrate on a small number. I'm using a 4 extra large. So the working set size for this workload is around 85 gig. That fits all in RAM. So whether I'm running tiered cache or regular, I'm going to get the same result because it's all just coming from the shared buffers. And that's what we see on the vertical or on the horizontal axis is how many queries are taking how much latency. So you want it far to the left, and you want it as high as possible on the vertical axis. So either one of these, we're getting about 0.23 milliseconds, very fast reads, right? But what happens if we quadruple our working set size, right? We got more than 300 gig now. We're going to get storage level latencies. So you can see that the line has a little bit on the cache side, right? But a lot of it is now coming from storage. And this gets to a 4x higher latency. So what's your choice here, right? You can buy a much bigger box. You can go to 16XL, right? Your boss isn't going to be very happy about that. Or you can suffer with poor performance, right? Or maybe tune the queries, which is probably usually the best thing, but that's not always possible. So What can you do about this? If you introduce the tiered cache, we now have the NVMe in the picture. So the purple line is the NVMe queries, and you can see that we have some coming from memory, and all the rest is coming from the NVMe. Because the NVMe is big enough, it's 4 times the RAM size, it all fits. So now we're only 50% higher on latency. So that is a bit of a jump, but probably not enough for your application to notice. And so with this technique, you can either take your existing system and make it much faster, or possibly you can go to a smaller system if you don't need the CPU and actually save more money for your company. So this is a really nice thing on manageability. When you're going to break up those monoliths and have lots of databases, you can actually possibly save on costs. So let's jump into sort of more details on breaking up the monolith. So let's go through my examples again. So we have our suppliers app. It's quite small. The first thing you want to do is you really want to make sure from a security basis that you're changing your permissions and what accounts you're using to prove to yourself that it really is isolated, right? Because you don't want to move it and then find out that someone was depending upon it. So the best thing to do is to make sure you've done that so that you're proving the suppliers are the only one using this. Once you've done that, we can move it. But remember, this is very infrequently used. It's only used like 5 days a week. It's pretty small. Boy, moving it to its own database seems like a lot of cost, right? This is where Aurora Serverless comes in. So this is a pay-per-use, second-by-second version of our system. So it's just another instance type. So it's not a different configuration. You just order db.serverless instead of an R6i. It scales up and down second by second for both CPU and memory. And the memory stuff is really fairly cool technology that we spend a lot of time working on. And there's no impact to the performance while it's doing this. And again, as I said, you pay as you go. So I'm showing Lambda here, but it could be any regular application. Just Lambda, obviously, and serverless kind of go together. So when your Lambda starts off, you need a little bit of memory and a little bit of CPU. But as it grows, you keep adding more and more CPU and memory, right? Until you get up to this using quite a lot. And we can go up to 256 ACUs, which is about equivalent to a 16XL now with serverless, so quite large. And it will shrink back down when you're not using it. And we just introduced in the last month the ability to scale to 0 on serverless. So for this application, we might be able to even turn the database off over the weekend if no one's using it and save even more money. So now that we've got our cost-effective solution, we're going to do a technique that's fairly similar to what Intuit did, which is we're going to fire up our serverless database. We're going to fire up DMS. We're going to start replicating that supplier data in, and we're going to get that database all caught up. And then we're going to stop doing updates. We're going to fire up the new supplier app, and we're going to start that up. And you'll notice what I've done with DMS is I'm doing that same technique that Ryan talked about where I'm replicating back to my original database. And this is in case I need to fail back to that because there's some challenge with the new application code. But if there's not, then shortly thereafter, I can just delete that and we can remove the data from the monolith. So that's pretty clear cut. But let's go to the more complicated one, which is the entangled solution, right? So we want to move the supplier app and maybe the customer app. So the first thing we're going to do is that same kind of security thing to try to figure out who's using what, do our analysis. So we find out that the supplier is actually, the shipping application is only using the customer data read-only. And that's the same for the ordering app, because they just need to read the customers. They're not actually modifying them. And same thing goes for the shipping data. The ordering application is just checking on where shipments are, right? So we've proven that it's safe, that these are entangled, but not on a read-write basis. So what we can do is we can set up, and I'm showing serverless here, but these can be provisioned, new databases for both customers and shipping and DMS, and we're going to replicate into those databases just like we did with the other one. And now we're going to set up new applications for those ones. Now remember that the customer data was needed by the shipping. Well, we're not going to have it access its data. We're going to actually build that through the new application, right? Just to simplify and separate out our microservices. So this is all working fine, but now we have a problem, right? Because what about that poor ordering app? It still needs access to those tables. Oh, do we have to move it at the same time? That's going to be kind of painful. No, right? We can reverse the replication and leave that long-term replicating from those new ones back to that monolith database until we take care of refactoring the ordering database. So once we do that, we could disconnect this. But until then, this allows you to do a stage by stage. So you could imagine if you had like 20 or 30, which in some days, in the old days in Amazon, we had more than 30 or 40 things in one database at a time. It was kind of crazy. So there was a lot of things that we had to separate out. We use this technique a lot to kind of move in stages because we didn't want to try to do a big bang that would have taken years. So we've gotten that done. We still have this challenge with our ordering database and our temporal data. So what we're going to do is, again, very similar to what Intuit did, that we're going to try to use different services for this kind of data, right? So in their case, they got some data to doing searching. We're going to do it in S3. So we're going to use S3 to store our older data. We take the last year's orders, and we're going to put those in one S3 item. And this includes all the order item details and all the information that we need to answer that query. So then when we can rewrite the application to do that query against S3. And even though you might think, well, S3's got a much higher latency than talking to a read on Aurora, you're right. But remember, we're doing one call to S3, not thousands of round trips to get blocks from the database, right? So this can actually be way more efficient, both on the application side and on the database. And of course, once you've done this, what you can do is you can remove all that data from your database, right? And that's going to make it smaller, more efficient, and more cost effective. So this is another good thing as you're going through and chopping up your monolith, is to think about how some of your other data can kind of temporarily, it can be different because now it's no longer needing to be written to, right? It's just read-only at that point. So we've gotten some pretty good work done here, but we still have the ordering database, and it's growing like crazy. So we're now worried about whether this is going to continue to fit. So we're going to move to a sharding model. And you can use something like DMS or some other method to essentially, again, replicate the data into a set of shards. And this is good, but as Narayan was saying, managing a lot of shards can be complex, right? But at least we have scale now, right? But we have a bit more of a burden. And what's part of that burden? Like, one of the burdens is resharding. So you do your initial sharding, you say, you make some guesstimate typically, and you're like, I think 4 is a good number. I don't know why it's 4 or 5, right? And you go, yeah, we're never going to need more than 4 of these. That'll be fine. And then, of course, this happens. One of them grows, and guess what? You're resharding, right? And this happens more than you'd think, because I think people's time horizons are a few years. And I can tell you, I've been at Amazon for 25 years, so any number I chose back when I started, I can probably tell you it was wrong, right? So consistency is the other issue with sharding, right? You have to start dealing with, if you want to add a column to a whole bunch of these shards, you have to worry about actually getting it right across all of them and making sure your application can handle it while you're rolling out these changes, right? If you want to do things like, tell me the number of open orders right now, it's going to be slightly inconsistent because it's going to run just slightly off on each one, right? Maybe it's okay, but that's just a challenge you have to know about. And backups is probably actually one of the bigger ones, because if you do any transactions across these shards, if you restore that, you're going to get slightly different things where you might have actually broken one of those cross-shard transactions across that time boundary. So this is pretty complex. The other one is capacity management. When you have a single large database, this is easy from a heap management perspective. You make sure the box is big enough to hit the maximum of your daily thing, and that's fine, right? But when you break things into tiny shards, the shards, typically the heat moves around depending on what customer's doing what, or where the heat is. And so what's hot in the morning might be cold, and then the other one's hot in the afternoon. And guess what? You end up just scaling up your shards, right? And because you have a lot of these shards, your cost may actually be quite a bit higher because you have more wasted space in all the shards. So our answer for this is Aurora Limitless. This is our sharding solution. You order an Amazon Aurora cluster just like normal, but what you do is you create a database shard group instead of an instance. And this is going to give you the distributed transaction router layer, and this is the thing that you're going to connect to. As its name implies, it does the transaction handling and the routing. We're not magic namers here. And you can see that the connections just go into your normal CNAME that you would normally use for your cluster, and it's going to connect to this routing layer. So it doesn't look different from your application. And that routing layer is going to route your queries down to the shards, and that's where you're going to get your answers from, and that goes back through the layer to your application. So this scales very well. In our benchmarking, we're above 2 million TPS, which is quite impressive. If you get a hot shard, we can do automatic resharding for you, or you can decide when you want to do that split. We use the serverless capacity that we have in our limit list for all these data shards and the routers. So as the heat moves up and down in the day, we don't have to reshard just because we grow up or down like 30 or 40%, because we can scale up to, like I said, 256 ACUs. And we have consistent query and DDL and backups because we use a global clock across this entire system. So when you issue a DDL, it's actually going to all of the nodes and is executed as one distributed transaction. So you don't have to worry about getting weird answers, right? And the same thing for your backups. When you ask for a backup, you know all the transactions will be exactly correct. So this simplifies a lot of things. You don't have to make as many changes to your application. So we now have our ordering application, but we've moved to limitless, and doesn't that look a lot simpler than having all those shards to manage, right? And it is. So we're doing nicely on our journey. We've got our ordering done. We've got our customers done. We've got our shipping done. And of course, we got that supplier app done. But what about analytics, right? We had that nice solution for analytics that was nice and simple. What are we going to do? Well, when you're doing analytics, typically on the one side, you've got your relational database for OLTP, and the other side, you have something like Redshift for data warehousing. To get that data in between, you typically have to build a data pipeline. It might involve DMS, S3, a bunch of different of our services. You probably have a data engineer that has to work on that. They have to monitor, make sure it's always running. This works, but it's complicated. So we thought we wanted to simplify this, and that's the zero ETL that Narayan was talking about earlier. So you can just set up a zero ETL integration from your Aurora instance to Redshift, and that's it. We're going to do all the loading, all the management, and the testing I was doing, you're getting like maybe 5 to 10 seconds lag on this, so it's very real time. So you can actually do your real-time dashboards. How do we do it that fast? Well, we actually do storage level work for this replication. So not only does it not impact your head node, but it's very fast and efficient. So we do parallel direct export here. We do that directly to Redshift. And for the CDC, we do that again from storage, not from the head node, and then we stream that to Redshift. So this is all very efficient and very fast. So we now have all of our properties, and we set up zero ETL. And you'll notice that I can set up zero ETL from many databases, up to 50, into a single Redshift cluster. So you don't have to have a ton of Redshift clusters for each one of these, right? So you can see that we've simplified. We do have more databases than we did in the beginning, but they're all running a really well-managed system, and most of the management is on the Aurora side. So this is kind of a good model for a journey that still allows you to get to that control of the microservice, get rid of all the problems you had with the monolith, but not end up with basically sort of, as I consider it, the microservice sprawl that you can kind of get into if you're not careful. So with that, we have some related sessions that you can check out. They're doing a great job this year. The videos are actually coming up very soon. For example, I think both the very first two are talks that I've given. There already videos are available if you want to look at them. The other ones, probably if they're not up yet, will be up very shortly. So check those out. And thank you, and thanks, Narayan. And that's everything. Please remember to fill out the survey form.